Okay, let me share my screen and we'll get started. Okay, so tonight we're going to hit chapter 9. We've done some of this. I'm going to finish up low um, frequency response. Then we're going to go to do the high frequency response analysis. And then we'll be done with bipolar transistors. As far as small signal model, DC operating point, small signal model, gain, we need to go over how to calculate the gain, excuse me, and also to calculate the low and high frequency poles. So I sent this out to class last week. Hello. Seems we have a problem here. Can everyone see my screen okay?
Yes, sir.
Okay, thanks. So I am recording this. So we had started looking at, I'm going to skip this first part for now and get straight to the transistor stuff. And then we'll come back and look at some of the actual Bodie plots, since we didn't do that as much as I would like to have done. So going forward, okay, let me zoom in a little. Okay, so we looked at before the frequency response curve for excuse me, for an amplifier. We call this the mid-range mid frequency gain region, where the gain is relatively flat. Excuse me. This low frequency pole location here is determined by our coupling and bypass capacitors, and its high frequency is due to internal junction capacitors, which we haven't talked about yet, but we're going to talk about that tonight. So here's a small signal model of a transistor showing our coupling. This is a bypass cap here. C sub C coupling capacitor for the load to the collector node, and CB coupling capacitor to the input or the base from our voltage source or signal source here, V sub S, with 1K source resistance. Okay. So we've done the small signal, DC operating point analysis before. And so this gives us, for this particular circuit, an emitter current of about 2 milliamp. And of course, IC is approximately equal to IE for this particular transistor. I think it's a 2N2222. Yep. It has a beta of like 180. So the collector current and emitter current is going to be pretty close to one another. What the author refers to as RB, or I guess big B, is R1 in parallel with R2. That's this parallel combination here. And then the input impedance of this amplifier is seen by looking into the base, and it sees RB in parallel with beta times RE. Okay. And then here on the output, this is the output node here. So I'm just going to walk through this quickly because we've already done this before. The lower cutoff frequency, there are 3 poles. Pole due to this bypass capacitor, this coupling capacitor, and this coupling capacitor. And we saw in one of the other analyses that this will be the dominant pole. So here's the cutoff frequency introduced by your coupling capacitor C sub B, this guy right here. And so the approach to this is when we have multiple capacitors in the circuit, we want to find the pole associated with this capacitor here. We actually short out the other 2 capacitors and then find the equivalent resistance seen across the terminals of this capacitor, CB. In this case here, it will be RS plus RN. RN is this this resistor in parallel with beta has RE plus RS, assuming that this voltage source is also 0. And so the resistance between across the terminals, this 10 microfarad capacitor is RN parallel with beta RE plus RS. Why is it plus? Well, we get here and we get a split from here to here. So these two are in parallel. This symbol here means that these two are connected to the same node, which goes back to here. And then to get back to this terminal of the capacitor, we have to go through RS. So our R Thevenin then is RS plus RN. If we plug in the numbers, we know RS, CB, 2 pi, and so then the pole associated with this 10 microfarad, is it 10? Yeah, 10 microfarad cap, we plug the numbers in, it's 6.2 hertz. Cutoff frequency introduced by the coupling capacitor C sub C. Here you notice in this drawing, only C sub C is in the drawing. C sub B has been shorted, and this CE is also not included. And so we find the Thevenin equivalent seen by this capacitor right here. We see between this node and back to here, we see RC plus RL. That's our Thevenin. The voltage, this dependent source here is basically 0. So this is basically an open circuit. So the only resistance we see is these two resistors right here. That gives our Thevenin of C sub C. And if we plug the numbers in this equation, we get the low frequency pole due to the coupling capacitor on the collector is 4 hertz. Now we have one left to go, and notice these are all the external caps that were placed in the circuit. Now, if we're looking at the cutoff frequency introduced by the bypass capacitor C sub E, so we've done the coupling capacitors CB and CC. Now we're going to do the bypass capacitor CE with CB and C sub C set equal to 0. And looking into this node, we see RE here in parallel, excuse me, with the resistance looking into this node. I'm sorry, go ahead.
Oh,
okay. Thought I had a question. So here's the question. Here's the equation for R Thevenin sub CE. Looking into this node, I see RE in parallel with what the author calls R, big R, low e, which is the resistance seen looking into from the emitter to the base. Okay. And that R little e looking from here to here is basically this resistance plus this resistance in parallel with this resistance divided by beta. And so we're done, we'll have beta RE divided by beta, we get RE. And then we have RB in parallel with R, so S divided by beta. And since we know all these values, RE, of course, comes from our GM, which we would have calculated earlier. So our Thevenin of CE is basically this equation here. Plugging our numbers in, we get 17.6 ohms. And now calculating for our Thevenin, excuse me. And so our low frequency pole, due to our emitter bypass capacitor, is given by this equation. They're all the same equation, 1 over 2 pi R Thevenin times C something. Plugging the numbers in, we get 90 hertz. So this capacitor on your emitter occurs at 90 hertz. And, excuse me, the pole on the, due to your emitter capacitance occurs at 90 hertz. So from high frequency to low frequency, this pole occurs first. That makes this the dominant pole. So the dominant pole on the low end is the one that occurs the highest in frequency. So just reading here, the largest of the three cutoff frequencies is the dominant or low cutoff frequency of the amplifier. As expected, the dominant cutoff frequency is the one introduced by the emitter bypass capacitor CE, which is 90 hertz. If this lower cutoff frequency happens to be too high for certain applications, the capacitor CE can be increased to obtain the desired cutoff frequency. If I make C sub E bigger, I'll actually push that pole lower in frequency. For example, if the lower cutoff frequency is specified to be a maximum of 50 hertz, then the size of CE has to be increased from 100 microfarads to 200 microfarads, yielding a lower cutoff frequency equal to 45 hertz. So we can adjust the location of that pole by adjusting the value of the capacitor, not by changing the value of the resistor. So here's a practice problem here. I think I assigned this to you already, haven't I? 9.93.
Yes, sir.
Okay, good. And then we look at another. So let's look at example 9.2. This is slightly different than one we've seen before. And the difference here is we have RE1 and RE2. So we have two series resistors in the emitter, and only part of it bypass. Okay, well, a second here. I need to do a little muting. Only the larger portion of it is bypassed by the CE capacitor, and this small part is still left here. So the question is, what does this do? So let's take a look at it. So we go through and do the small signal, DC operating point analysis. We get IE is 2 milliamp. We can calculate little RE, which is 1 over GM of 13 ohms. Beta is 180, so times RE gets us about 2K. Calculate our RB, which is R1 in parallel with R2. And R little b, which is beta times little RE plus RE1, is about 5.9K. And here's our input resistance calculation. So here's our small signal model. Our signal source input impedance, source impedance. Here's our RB, which is R1 in parallel R2, which we calculated, beta times RE. So our small signal model looks like this. So what happens to our F? So our lower cutoff frequency due to C sub B here is given by this equation, RS plus RN, same equation as before. It's about 4 hertz. Excuse me. The cutoff frequency introduced by the coupling capacitor C sub C, this guy right here, is given by this equation. It's about 2 hertz. Now the cutoff frequency introduced by the bypass capacitor, this C sub E. So what changes here is our R Thevenin is going to look a little different. So our R Thevenin from here is going to be RE2 in parallel with RE1 plus beta RE, and this divided by beta. So this gets added to the resistance seen here. And when we're done, we have R Thevenin is 42 ohms. And now we have a F LE, the pole due to your emitter bypass capacitor, is now 38 hertz when before it was 90 hertz. So we can actually move the location of this dominant pole also by either changing the value of the capacitor, or in this case, we just split the resistor into a 1K and a 24K ohm resistance here, and we're able to adjust the location of our low frequency pole. What this also does, and I didn't show this to you before, this guy here also decreases your gain. So what we do so we're splitting this up cause our low frequency pole to move lower in frequency, which increases what we call the bandwidth. So we can go lower in frequency than we did before. What we get from that also, though, is by increasing the bandwidth, we get less gain. Before, our gain was, of course, this is beta IB. I use GM times, I use the transconductance GM here instead of beta IB, which is equivalent. But before it was GM times RC in parallel with RL, when all of this was bypassed by the capacitor. Now it's actually RC over RL divided by 1 over GM plus RE. So it adds, let me draw this for you, or write it out for you. And let me switch screens. Okay. So what we had before, when we had a circuit that looked like this, and here all of the RE resistance was shorted by this RE, CE capacitor. The gain then, A sub B, was the magnitude of it, was GM times RC in parallel with RL. GM is 1 over RE, so let's write it like that also. So it's RC in parallel with RL over little RE. If now we have that resistance here that was not bypassed, so I'll redraw the circuit. I think it was RE1. C or L. This is the output. Now the gain, should be out over Bn, the magnitude of it, is RC in parallel with RL over RE plus RE1. So by not bypassing RE1, you actually add it to the denominator of your gain expression, which decreases your gain. But what it does for your F sub LE is it causes your bandwidth, causes your FLE to decrease or go lower in frequency, which causes your bandwidth to increase. So if I wanted to, just as adding this in and not completely bypassing it, adjusted my low frequency pole, it also adjusts, or in this case, decreases my gain. So if I had more gain than I wanted, rather than changing out the entire value of that resistor, say instead of going from 1K to 1,024 ohms, I would just take the 1K and split 24 ohms off from it, only bypass part of it, and then that would decrease my gain if I'm getting too much gain, resulting in distortion at my output. So there's at the back in here in chapter 9, it gives you what's going on here? I'm sorry. Gives you equations for these two cases. Let me scroll to that for just a second, and then we'll come back to the upper frequency gain. Let's see if it's here. Here we go. So on page, come here, page 374 of your handout, for your low frequency analysis, here are all the equations that we're looking at the book. So the frequency due to your C sub B capacitor, this is its pole location. The cutoff frequency due to your C sub C coupling capacitor is given by this equation. Cutoff frequency given by your C sub E, which happens to, in all these cases, to be your dominant pole, is given by this equation. And so it says with a single unpassed RE, we have this for R Thevenin for R Thevenin CE, this guy here. If it's only partially bypassed, which means some of that little RE is split into RE and RE1, RE1 and RE2, then R Thevenin now is RE in parallel with RE1 plus R little e, where RE little e, this guy here, is given by this equation. And so here, the dominant low frequency cutoff frequency FL is the highest of the above three cutoff frequencies, which is usually FLE because of the very low resistance seen by CE. So your CE capacitor usually sees a very low resistance, and lower the resistance, the higher in frequency is going to be compared to the other poles. Okay. Next, we're going to look at high frequency analysis, and this is all given due to, capacitances within the transistor itself. And so there are actually two poles associated with capacitances and one associated with your beta roll off or your gain roll off of your transistor. So let's get to that real quick. Yeah, we'll come back to those practice examples. So this is going to be a little bit of math, but it's important for me to walk through it. I just want you to understand, to see it and understand, and hopefully understand it, but I won't be asking you to do it. But to get out of this class and say you've never seen it would be negligence on my part. Okay, so we have, I gave you practice problem 9.3 to do. I think, yeah, I think we'll give you 9.4 also. Haven't assigned it yet, but you will get it before the night's over. So the upper cutoff frequency.
No, sir, you didn't give us 9.4. You gave us 9.3.
I said I have not, but I will give it to you before the night's over with. You'll get 9.4 also. I said I have not, but I will give it to you before the night's over with. You'll get 9.4 also.
Okay.
Okay, no problem. Okay. Yeah, if I misspeak, please correct me. So the upper cutoff frequency again is due to, I'll just read what's here. The drop in the gain of the amplifier in the high frequency range is caused by the transistor internal junction capacitance C sub BC and the diffusion capacitance C sub BE, as shown in figure 921. So we're figure 921 over here. So most of you, if not all of you, are electrical engineering students. I assume you've taken semiconductor devices. So here's our circuit. Our base emitter junction here, we draw it as a diode. There's literally a diode junction here, a PN junction. Well, whenever you have a PN junction, you also have capacitances associated with it. So you have a C sub BE capacitance that's across your base emitter junction. There's also a diode junction between your base and your collector. And if you have a diode junction, you have capacitance. So this is C sub BE, internal junction capacitance from the base to the collector. So what happens as a function of frequency? Well, the way this circuit is supposed to work is, as I change the frequency of my input source here, this signal comes here, okay, causes base current to flow, and the base current gets multiplied by beta, which causes my current here, the signal here to increase as a function of frequency. Because this capacitance is here, all of the signal here is coming into the base does not get amplified at the base emitter junction. Some of it actually bypasses that and goes straight to the output. When you start going straight to the output, it doesn't get magnified anymore, so you don't have any additional gain. You'll actually start to get less gain. Okay. So in a nutshell, that is what's going on with this device here. If this was semiconductor devices, I would go a little more detail of it. It'll go into a little more detail, but it's not. So let's take a look at, now we need to draw the small signal model. How we drew the small signal model of this transistor and all this stuff here around it with these coupling capacitors and bypass capacitors. Well, we have two more capacitors here to add to the small signal model. And I will go straight to that first, and then I'll come back to this. So here is the small signal model. Here's your base, here's your collector, here's your emitter. Between your base and your collector, there's this capacitor, which wasn't there before. Between your base and your emitter, there's this capacitor that wasn't here before. Okay, so this is what our new high frequency small signal model looks like. And well, I'm going to go ahead and mention it, then we'll go back and look at the detail, go over some of the details of it. This circuit here is equivalent to this circuit here. Question is, what happened? Well, we no longer have C sub B across here. But what we have is we still have C sub BE. We no longer have C sub BC across here, because we now have a capacitance we call CMI, C Miller N, that gives this circuit the equivalent behavior as if we had this capacitor across here. But we actually, what we do is we take this capacitor, split it into two pieces. One, how it loads the input, C sub MI, and how it also affects the output, C sub MO. All of the rest of this is same as before as far as the small signal model goes. So let me go back and let's walk through a little of this math for what's called a Miller's theorem. So Miller's theorem basically says you have a circuit that looks like this. You have some gain, so you have an input here and you have a gain, and you have an output, and you have some impedance connecting your input to your output. That circuit can be redrawn as the following. You still have your gain, but rather than have this impedance now connected between input and output, you have the effect of this impedance here on the input given by this element Y sub 1, and the effect that this impedance from the input to the output has on the output given by this impedance Y sub 2. So we take this circuit and we can actually make it look like this circuit. And the math that goes through, here's the math that we actually go through. And the guy who came up with this was a fellow by the name of Miller. And the Miller effect basically says any impedance across input from the input to output of across some gain element can be redrawn as this circuit right here. And it makes it a little easier to be able to do the calculation algebraically, because we don't have to be concerned about this path here, but we still have the same effect that this path has by adding these elements to the input and output. And so what is that element? Well, it could be anything. It could be a resistance. In our case, though, it happens to be this capacitance C sub BE. C sub BC, excuse me. And by walking through this, we have this impedance, or, well, 1 over impedance or admittance here. If you replace this admittance Y with the admittance due to a capacitor, which in our case it actually is, then what we get is, this is what the impedance of the capacitor is, J omega C. But if we replace that one capacitor with an admittance on the input and output, the input admittance will be given by J omega C sub B, should also equal J omega times C times 1 minus A sub M is the gain, the mid-band gain that we calculated before. And so now dividing both sides by J omega, we get now that this capacitance on the input, C1, is the same as the capacitance that was from the input to the output multiplied by 1 minus the gain. And we call that C Miller N. Now we look at the output circuit. We have a similar thing. We have this impedance or admittance Y2. This admittance Y2 equals the admittance of the original element connected between the output and the input times 1 minus 1 over the gain. Actually, I said admittance, actually susceptance. So we have a circuit that looks like this with a capacitance from input to output from V1 to V2. We can make it look like this by taking this capacitance and multiplying it by 1 minus the gain and placing that value on the input of this network, and then taking this capacitance and multiplying it by 1 minus 1 over the gain and place it on the output of this network. And then we have the same effect as if we had this capacitance between V1 and V2. And so these CMI, C Miller in, and CMO, C Miller out, are called the Miller equivalent capacitances. So, well, let's look at the numbers and we'll see what's going on. So here's back to where we had jumped ahead. We took this C sub BC here, and using that Miller's theorem is what it's called, we have a C sub MI and a C sub MO. If we do the calculations, so here we have a gain of minus GMR prime, which is about 136. So I have a gain of 136 magnitude wise, or 43 dB roughly. So to calculate C Miller in, it's C sub BC times 1 minus the mid-band gain, A sub M. So we get C sub BC from your data sheet for your transistor, it's 4 picofarads, times 1 minus the gain. Well, the gain is actually negative here, and so it actually becomes 1 plus the gain. So C Miller in then becomes 4 picofarads times 137, or 548 picofarads. So the input Miller capacitance looks like this capacitance here multiplied by the gain from the input to output. And then C Miller out is C sub between your base and collector times 1 minus 1 over the gain. Well, 1 over the gain is going to be pretty small. And so you'll find that C Miller out is approximately equal to C sub BC, in this case about 4 picofarads. So now we can return to our small signal model. We have now this thing called CN. Well, what's the CN? Well, we have CBE. Oh, let's go back up here for a second. Here we go. We have C sub BE, and because this C sub BE is in parallel with C sub MI, we can just combine those two, and we just call it CN. Okay. And then here on the output, all we have is C Miller out. And we just call it C out. So CN then is CBC plus C Miller in, and C out is C Miller out. So CN is see what 8 picofarads what CBE was, plus 564 picofarads C Miller in. So this becomes 572 picofarads for CN, and then C out is just approximately, well, it is C Miller out. C out is equal to C Miller out. So this is just 4 picofarads. So now what do we have? We have a capacitor here, and we have a capacitor here. And just as in the low frequency case, now we can find the pole that's associated with this capacitor, and then we find this pole that's associated with this capacitor. So this F sub HI, which is the high frequency pole due to the input capacitor, is 1/2 pi R Thevenin C sub I times C sub I. And the high frequency pole associated with the output capacitor, F sub HO, is 1/2 pi R Thevenin CO times CO. And if we look at this, R Thevenin CI here is going to be basically just beta RE in parallel with RB in parallel with RS, which is 611 ohms. And then R Thevenin due to, or seen by C out, R Thevenin seen by this capacitor here. Remember, our dependent source goes away, so it becomes zero current flowing through here, which means it's an open. It's just RC in parallel with RL, which is 181.83 k ohm. So we do our calculations. So our high frequency pole is approximately equal to a high frequency pole due to your Miller input capacitance, which we put the numbers in, we get 455 kilohertz. And your high frequency pole due to your output capacitance is 21.75 megahertz. So our upper bandwidth then is 455 kilohertz. This pole occurs first in frequency. This one appears higher in frequency. So we have one other pole though. Frequencies F sub B and F sub T. Important high frequency parameters of bipolar transistors are frequency FB and F sub C, or F sub beta, excuse me. To derive an expression for the short circuit current gain F sub beta, consider the transistor shown in 928. So we have our current gain beta also rolls off at high frequency. And this is a test circuit that shows how we're going to calculate it. And so the high frequency pole due to roll off at beta is just 1/2 pi R sub little b times C sub B E plus C sub BC. Here's C sub BE, here's C sub BC. Okay. Here's our little RB, which is beta times RE. So the pole seen by this capacitance here is this resistance. And so our upper cutoff frequency due to our current gain rolling off, or F sub beta, is 5.67 megahertz. Okay. So let's see, can I find it? Nope, it's not here. So let's switch back to the document camera for a second. Let's talk about this for just a second. Okay. This is not fun, but it is necessary. Let's see here. There we go. So we have our transistor amplifier. Here's our frequency. Here's our gain in dB. And let's say we have our mid band gain is here, whatever it happens to be. And then at some point, we have a low frequency pole that kicks in. right about here. This is F sub L, and the slope of this line here is minus 20 dB per decade. And then let's say we have another pole. So this is running along here. And then we have another pole that shows up. We call it FL2. And it adds to this slope another 20 dB of roll off per decade of frequency. So it'll change the slope like this. So this is now minus 40 dB per decade. And it'll continue like that until we get to our third pole, which may be located here. And then they'll roll off at minus 60 dB per decade. So each pole decreases the slope by minus 20 dB per decade. For a decade, it's a factor of 10. So we have the same thing here at high frequency. Our first pole that kicked in here, this rolls off at minus 20 dB per decade. And then at some point we get a second pole that's located at this point frequency. And now this slope changes to a minus 40 dB per decade. And if we have another, if we go higher and higher, this F sub beta roll off will make it roll off at minus 60 dB per decade. So if you're given say low frequency poles FL1, FL2, FL3, and high frequency poles FH1, FH2, and FH3, you should be able to do the voltage plot showing the appropriate slope of the gain versus frequency.
Can you give permission to record for this Zoom meeting?
I'm sorry?
Can you give permission to record for the Zoom meeting?
Oh, I'm recording.
Okay.
Yeah, I don't have it set automatic. I started it at the beginning of the class. Yeah, we're 46 minutes into it and going. At least I hope so. I thought I did. So there we are with our Bodie plot. So we got a whole lot of things going on here. So let's go take a look at something. We have what? We have an amplifier. So we have an amplifier. Just a simple one transistor amplifier with what, 4 resistors and 3 capacitors, but a whole lot of stuff that goes on with that. From this, we do what? We determine low voltages, VB, VE, VC, and from that we get IE, IC. And because this is a voltage divider bias, we don't really concern ourselves too much with beta, but we can get beta if we wanted to. But this is beta independent if it's designed correctly. So we get our we get these low voltages and currents, and then from there we can get our DC operating point or Q point. Which is what? VCE and IC. Once we get that, we do our small signal model. And from our small signal model, we can calculate our voltage gain. If we want to, we can do our input impedance also, Rn, and even our output impedance. And then from there, we get our frequency response. So we get our low frequency poles and our high frequency poles. And from that, we get our bandwidth, which is F sub H minus F sub L. So on one page, that's what we've been doing since the semester started. So in addition to calculating this, we can also then draw the Bode plot or A sub B, the gain versus frequency. Questions or comments? So this is a summary of everything we've done since day one. So how do you get all this? So number one, these are the steps from your circuit. These are your steps in that order. So we got to do this, and from this we get this, and we get the DC stuff. We do our small signal model, get our gain, our input impedance, whatever, and then from that we can calculate also our poles. So due to our capacitors C sub E, C sub B, C sub C. That gives us our low frequency stuff. Now, high frequency, that's due to C sub BC and C sub BE and anything else. We also deal with beta, F sub beta, how it rolls off. Oh, let me mention this when we're talking about the beta rolling off the gain. So we talk about the beta of transistors. If it lasts forever, it doesn't. It has some bandwidth also, and that's what we see at high frequency. So click here. So our frequency here, here's our current gain beta. Well, beta doesn't stay flat forever. At some point, it'll start to roll off also. So this is what gave us one of the other poles that wasn't associated with either an internal capacitance or an external capacitance. But the beta starts to roll off as functional frequency. You may or may not have covered that or tested on it in semiconductor devices. But unless you're going to be an IC designer or a device designer, you probably won't see this again. But because this is electronics, you are expected to be able to do analysis for a single transistor amplifier like we've gone through. Oh, and one other thing, I think I sort of mentioned it to you before. So we have our transistor here. Remember, so let's talk about our gain. Our gain then of this circuit is approximately the impedance seen looking out of my collector, which this is RL, R sub C, and this is my load R sub L, divided by the impedance looking into this node here. With this totally bypass, all we see is this little thing called R sub little e. Remember, R little e is 1 over GM. So then my gain can be written as GM times RC in parallel with RL. Or it could be written as RC over little RE. There's value to writing it both ways. For me, when this is completely bypassed, it doesn't matter. I can do GM or I can do RE. When it's not completely bypassed, it reminds me that if I have some of this still like RE1, then my gain becomes RC in parallel with RL over little RE plus RE1, this portion of RE that's not bypassed, or RE2, whichever part is not bypassed. So sometimes you might want to write it like this, but in general, the gain in this amplifier is approximately the impedance, the resistance looking out this node divided by the resistance looking into this node, RE. And so these are just values on the schematic. And if you calculate RE, which is 1 over GM, then you can do a quick estimate of what the gain of this circuit is without calculating all these operating points and things, assuming that everything is biased up right. You know, I can't go in here and make this resistor way bigger than it should have been, like 10 times, and this whole thing collapses. Now, you will still have VE equals VB minus 0.7. But if this resistor is much larger than it should be, this current here going through here will take this node and push it down so far that you're actually outside of your active region for your transistor. That's something that when I took this class, I remember Dr. Davidson always harping on, always assume that you're operating in the active region, and then verify that you're operating in the active region. Active region is basically the base is greater than the emitter by 0.7 volts. We know that. If that's not true, then the transistor's not on. But also, this voltage here cannot be more than 0.7 volts higher than this one. If it does, it pushes this guy down, and this diode right here actually starts to conduct. And so we're not acting like an amplifier anymore. So say for example, this was I think for one example in class, this was 2.66 volts, so this was like 1.89 volts, and this was like 9 volts. Well, 9 volts is greater than 2.66, so this diode here, which we never draw, but sometimes it's good to know this diode junction, this is greater than this, so this diode is actually off. So you're in the active region of operation. Right? And I know that was drinking from a fire hose, but I think everybody was thirsty, so I decided to hit you with it. Yeah, right. Okay, it's 7:28. I've been going for about an hour. Let's take a short break and see if there are any questions about anything. So it's 7:28. Let's come back in 7:33 by somebody, well, 5 minutes from now, whenever that is, by your watch. And let me know if you have any questions about anything. So take a break for a second. Okay, I have returned. Any questions about anything that you come across so far? Okay, so everybody's good. which means I can have that exam on next week and everybody's ready for it.
If you can say what everything's gonna be on it.
Sure I can. Everything I just said.
Oh, I got a question.
Ah, okay. Go ahead.
Uh, I had one question on the home. I know I had to text you and ask you this, but I was trying to figure out like how do I go about finding FL? Because I can find every other value, so I just don't understand how to find FL.
Remember, there are three. Hold on, let me go back here. One second. One second here, finding, show you in the notes. There we go. And where are you? Share. Okay. So on the screen here, let's go back to the beginning. So this is, I mean, it's configuration is exactly the same as probably I gave you. And you're asking for what is FL? Well, in order to get FL, you have to find the pole associated with this capacitor, the pole associated with this capacitor, and the pole associated with this capacitor.
Sir,
Yeah, I can't see
I
anything.
can't see nothing.
Okay. Let me see, where is my screen? Please move window away from the shared application. Which window? One second here. Gotta find which of these screens it doesn't like. Okay, let's stop sharing for a second. I have too many things up. There we go. And can we close this? Here it is. Okay, can you see my screen now?
Yes, sir.
So where was I? Here. What's going on? Okay, so we have common emitter amplifier like this. We have a coupling capacitor here, coupling capacitor here, a bypass capacitor here. The low frequency pole is caused by one of these capacitors. It won't be a surprise, it's actually this C sub E right here. How do we get there? Section 9.3.1, the lower cutoff frequency S of L. So you calculate your pole due to this B, C sub B, and you get 6.2 kilohertz, excuse me, 6.2 hertz in this example. And then you do the same thing for C sub C, and you get 4 hertz in this example. And then you calculate your FL due to your C sub E capacitor. And in this case, you get 90 hertz. So in this case, F sub L is the highest of those 3 low frequency poles, which in this case is 90 hertz.
See, if you go down to like, can you scroll down to the practice problem 9-3?
Sure.
So so like I found FLB, FLC, FLE. So I get what you just said, it's the highest, but like, so why is FL 85? So shouldn't it be 69?
That's a good question. That doesn't sound right, does it?
Yes, that's why I was saying I was real confused on the homework because I read the book and it said that, so I didn't understand why it was 85.
Sounds like an error because it only should be. Yeah, if we were going to do FLB, FLC, FLE, and then go FL then should be 69, not 85. Yeah, that may be an error. Well, I think, well, not maybe, it is an error. This FL is not 85, it's 69. So I think this is an error here. Because there are only 3 frequencies. And FL is by default the highest of those 3. Okay. 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 Did that answer your question?
Yes, sir.
So let me make this comment that I've made in previous classes. Just because the book has an answer doesn't necessarily mean it's right. You work it according to the equations, and the answer is what it is. If the book has something different, and I'm going to look at your work, and if your work makes sense, you haven't made a mistake, then you get credit for it. If the book is wrong, then the book is wrong. There are some errors in here. I think this is one of them because I don't know why F sub L would be 85 when you only have 3 poles. It has to be one of these 3 right here. Okay. Other question. So look at example 9.2, because that's an example of not having all of your emitter resistance bypass. That's going to affect your FLE and thus your F sub L, but it will also affect your gain right here. It will make your gain less. It will make your FLE lower in frequency, which will in effect increase your bandwidth of your amplifier, but it'll lower your gain, your mid-band gain. Okay. So here's an example of how to work a problem with not all of the emitter resistance bypassed. And then here's the practice problem, 9-4, for you to do it. You'll notice here that they don't have, so they have FLB, FLC, FLE answers, a voltage at mid-band, and voltage at, okay, interesting. That's be a cool one. Analyze and determine the low frequency cutoff amplifier, also determine the mid-band gain. The output voltage at mid-band and at the cutoff frequency. Beta's 160. Okay. So let's talk about this problem for a second, because I am going to give it to you. This is an assignment, practice problem 9-4. So we talk about calculating what the gain is. In this case here, we actually give you an input signal value of 100 millivolts peak to peak. And ask, see, what does this ask for? What is the gain? Determine the mid-band gain of this circuit here. And then ask for the output voltage. Well, the gain is V out over Vn. And if I know the gain and I know Vn, then I can calculate V out. V out is just the gain times Vn. So the output of this circuit then will be 100 millivolts peak to peak times whatever you calculated for the gain of this amplifier circuit here. Let's see, what's the other thing? It asks for the output voltage, yeah, and then the cutoff frequency. So then the cutoff frequencies will be, you'll need the, calculate your pole due to this capacitance, this capacitance, which will give you your dominant low frequency pole. And at the cutoff frequency. Okay. I didn't cover that with you. The last part here, when it asks, what is the voltage? The voltage at mid band, that's just the normal gain times the gain times Vn gives us the voltage. And at the cutoff frequency, let's go back and talk about what the voltage looks like at the cutoff frequency. So this is a frequency selective network. It's sort of like your amplifier itself. It has a maximum gain of 1. Okay. So here's my input. It has some output. And as I change frequency, at some point, my gain starts to drop. In this case, this is my cutoff frequency. And that cutoff frequency is given by the capacitance and the resistance that it sees. Okay. At the cutoff frequency, the output or the gain is only 0.707 of the midband gain. So in this case, the midband gain is 1. 0.707 times 1 is just 0.707. In this problem down here, it asks you what is the voltage at the midband, at the cutoff frequency. Well, it's 0.707 times the gain times the input. Let's see if I can find it. Here we go. Look at this graph here again, also in a little more detail. Here's your mid-band gain, A sub V, whatever, obviously A sub V sub mid, whatever that happens to be. And then here at your cutoff frequency, the gain is 0.707 times A mid on the low frequency, on the low frequency, and also the high frequency is 0.707. So when the gain drops to 0.707, either high in frequency or low in frequency, that determines your F sub L on the low end, your F sub H on the high end, and F sub H minus F sub L is this thing we call your bandwidth. Let's see. So for example, what was it, 994? So here in this problem, it asks for the output voltage at midband. That'll just be the gain, which you calculate here, times the voltage here. Roughly. Not quite true, but close enough. And then the that'll be your output voltage. At your cutoff frequency, then your output voltage would be 0.707 times the value that it was at midband. Because that's when it starts to roll off, your gain rolls off from a maximum value to 0.707 of that maximum value at your cutoff frequency. Okay. Other questions? So I'm going to need some more problems to work. Today is Tuesday. Yep, today is Tuesday. And they will be due, I would say, Monday. And let's look at having an exam next Wednesday. So instead of lab next Wednesday, we will have our first exam. And we will have lab tomorrow on campus. Because what we're going to do tomorrow, the circuit we built last week, we're going to build it again. And then we're going to look at the frequency response of it, the gain and the frequency response. So last time we just looked at the operating point and compared that to what was done with LT Spice as far as simulation goes and hand calculation. Now we're going to look at with our capacitors in place, and we're going to ramp up the frequency and look at the gain as it changes as a function of frequency. So that will be tomorrow. Come rain or shine. But if the weather gets too bad, then we won't do it. But if it's just raining, yeah, we'll be okay. So let's see what else we have.
Oh, when's the horn do again?
The ones I haven't assigned, Monday.
Okay.
I'll send you an email with the problems and when they're due. So you need to do at least, was it 9-4? And see, practice problem 9-4. And you have the exam, excuse me, the example problem 9-2. If I give you a practice problem right now, there will be an example problem that goes with it. That's in the book. And so there's example problem 9-3. 9-4. Practice problem 9-5. And also in this reading material I gave you, page 374, these are all of the equations that you'll need to do your low frequency analysis and your high frequency analysis. However, if you don't know what they mean, that means you need to do some reading. And see, overall frequency response. See if there's something else I want to cover here. Yep, there's something else I want to cover here. So, section 9.4, overall frequency response of the common emitter amplifier. So here's the common emitter amplifier, same as we've seen before. Here's our DC and mid-band analysis, low cutoff frequency, upper cutoff frequency. And here's our plot of the gain as a function of frequency, showing all of the poles. And remember, as I pointed out earlier, in our mid-band is relatively flat. At a high frequency roll off, it starts to roll off here at 20 dB per decade, where a decade is a factor of 10. So here it looks like this is 10 to the 5th here, and 10 to the 6th here, and 10 to the 7th. So that should drop 40 dB from this point to this point. Excuse me, 20 dB from this point to this point, 1 decade. And then it continues that slope until we encounter another pole, which causes the slope to change by an additional 20 dB per decade, or for a total of minus 40 dB per decade. Same thing on the low end. Our high frequency, our F sub L starts to roll off at 20 dB per decade, minus. Yeah, that should be minus here. And then when it counts this next pole, F sub LB, it increases by another 20 dB per decade, the slope. And then F sub LC, it increases by another, so it's minus. So we're going 20 to 42. Let's see, 20 dB, 40 dB. This is wrong. Oh, wait a minute. No, it's not. I see what's going on. That's something we're not going to we're not talking about in this class. There's actually something called a zero, which causes the slope to actually increase, but we're not going to cover it in this class. We're just going to look at the poles. I was wondering why that was a minus 60. Yeah, right here, there is what's called a zero associated with this C sub E capacitance also, and RE. Yeah. So I'll send this you an email, but practice problem 9.4, practice problem 9.5. There are example problems for each one of those immediately preceding them. And read section 9.4. Overall frequency response to the common emitted by the polar junction transistor amplifier. So if I gave you poles, if I just gave you these values, F1, F2, F3 of some value, and a mid-band gain of say 100 dB, you should be able to plot this drawing with this being 100, and then your lower frequency here is showing the proper roll-off. Okay. But that's why I want you to read section 9.4, and then we can talk about that next Tuesday if you have any questions, or before then. But the material basically ends at page 376. Those other amplifiers are different topologies we're not going to cover. They're useful, but not in this class. Well, not for what we want to cover in this class. I've actually spent a lot of time on the bipolar transistor amplifier and the frequency response, more than the class was supposed to cover, because as soon as we finish this, we're going to switch over to the MOSFET transistor, look quickly at its DC operating point, and do all of this all over again. But I know you probably hadn't seen this in the detail. It should have been covered in Electronics 1. That's why I want to spend the time doing it. Okay. So what else? Questions? And this is due Monday.
So we gotta have 9.4 on which one by Monday?
Practice problem 9.9-4 and practice problem 9-5.
Okay, you said you're gonna email them to us, right? As well.
That's correct. Yes.
Okay.
Actually, as soon as we get off here, I'll send out an email with the exact problem what I just told you and when to do. And
Okay, thank you.
be familiar with this these equations on 374. Those are the equations that you use. I haven't decided yet whether or not you get an equation sheet, because all of these work exactly the same. It's a resistance and a capacitance. You usually have to choose the capacitance and find the associated resistance that goes with it, multiply it together, and you're done. So all these work exactly the same. My hesitancy to give you these equations, some people are going to use this equation as a crutch, and it's going to break on them. If you understand how we got there by going through the example in the book again and say, okay, where's C sub B? Where's the resistance associated with C sub B? If you understand that, you don't need these equations. If you don't understand it, these equations are really not going to do you any good. I haven't decided yet whether or not I'll give you this or not, but we'll see. But be prepared not to have this a week from today or a week from tomorrow. Wow. Yeah, that's about right. Okay. And I think that's all I wanted to cover for tonight. Any questions about anything else? There will be lab tomorrow, as I said, on campus. We're going to rebuild that circuit and do the frequency response measurements on it. So if nothing else, that's all I have. So everyone have a good night. Text me or email me if you need anything. Let me stop sharing this.
What classroom we gonna be? You said we gonna be in person tomorrow?
Yes, in the lab. Tomorrow's lab.
Okay. All right.
Was it 6 o'clock?
Yeah.
Are you sure? That didn't sound very convincing.
Yeah. I know we do 6 o'clock in person, or you do 6:30 on Zoom. So I'm pretty 6 o'clock.
Okay. No, I just want to make sure that that we're okay with the time and no one's confused. So, all right, I'll see you tomorrow then.
Wait, was there an option to do 6:30?
I'm sorry.
Was there an option for 6:30?
Not really.
Oh, okay.
Remember, that's a very long day for me. And no, let's do 6. And we'll see where we go from there. Because at the end of the day, we need to finish the lab before it's over with. Otherwise, I'll leave you in there. So nope. Let's do 6 in person, and yep, let's stick with that. Okay.
Okay.
All right. Email me if you need anything. I'll see you tomorrow evening.